And I'll share screen on this one. All right. So, hi everyone. Sorry about taking so long to get started here. But yeah, that's right. So today's discussion, we're going to be talking about stacks, queues, lists, and debugging. So our objectives for today, if anyone can't hear, by the way, just let me know. Our objectives for today is first, we're going to talk about technical interviews. So for example, if you're interested in like getting a job or an internship in computer science or like software engineering or anything like that, you'll probably have to go through some technical interviews. And so we'll go over kind of what that entails. Then we'll talk about project one breakdown. I don't think we're going to do quiz review, although if you guys have questions about it, we can. Then we're going to talk about stacks, queues, and lists. And then if we have time, we'll do these. Okay. So first and foremost, right, how to prepare for technical interviews. So for these, we're having a session or multiple sessions, and it's called TIPS, so technical interview preparation sessions. And you're going to practice live interview, technical interviews, and it's going to be on Zoom. It's going to be bi-weekly. And another nice thing about it is you can use it to replace Higher Gator. So later in the semester, we have like Higher Gator quizzes, and you can attend 2 of these TIPS sessions to replace it. And they really are pretty helpful and kind of nice to go to. So I suggest if you can, go ahead and go to the TIPS because, I mean, why not? As long as you're available at that time. If you're not, then of course. Okay, so how to start project one. So for project one, we're going to be sending out a breakdown of it, I think, yeah, later this week. So on Thursday at 2, you'll have some TAs who will give a presentation on how to start it, which is kind of nice. I think there are 3 of them for this one who will give a presentation on it. Yeah. And I think it'll be recorded, so you can always watch it later. So quickly talking about technical interviews. So what are they like? So for more information about them, of course, you can go to like the tip sessions. But briefly, yeah, of course, first you want to do your research on what the company's interview process is like, because if you don't, then maybe they'll ask a question about themselves and you'll be like, I don't know. Not that that's ever happened to me, but yeah, don't do that. Yeah, so yeah, they can ask a system design question or data structures and algorithms question. So honestly, that's one of the things that's really helpful about this class. It really prepares you for what those will be like. And there will probably be multiple rounds of interviews. So you'll have like behavioral and technical. So behavioral is more like they'll ask you about yourself and your like soft skills maybe, and then technical will be more like data structure and algorithms questions. So kind of like what you'd have like on STEPIC, for example. And they'll give you a question, probably orally, and it's good to ask clarifying questions so they can kind of see your thought process. So a lot of times you want to walk through an example and talk about edge cases. And yeah, make sure like clarifying questions are really good because it helps them see like what you're thinking. Because that's the main idea. It's not for them to see you solve the problem. It's for them to see like what's going on in your head. And then you describe your solution. And then, yeah, for more comprehensive, we'll go to the next slide. And then at the end, you usually ask questions. Okay. So generally for technical interviews, the flowchart is like this. You listen to their question. You go through an example, you get test cases for the example. Like this helps you understand the problem better, really. And then you ask questions, right, to clarify. And then you go brute force, is usually the first place to start. Like, for example, if you don't know the optimal solution for it, a good way to start is just like, okay, what's a solution for it? It doesn't have to be optimal, but like, what's a solution? Maybe you just like go through every possible combination. Maybe that's not what you want to do, but you brute force, right? And then maybe there's a better way to solve it. And so then you kind of say, oh, okay, we can improve it. And then you make the optimizations. And then you walk through your code or like if it's technical interview, you walk through the code, if you have to write code, and then you review. And then you implement it. So then you actually write the code, right? And then you test it. So you go through some test cases. And yeah, that's our source for this. Okay. So that's just a brief overview of that. Yeah, for more information, of course, like tip session. That's it. Okay, moving on. So today we're talking about stacks. So what are stacks? So stacks are a data structure that are really, really helpful. So you might hear stacks and think something like, oh, maybe you've heard of like the call stack, right? like linear is recursion. And that actually is also a stack. It's an example of a stack. Because what a stack is a data structure. It's an abstract data type, and it's a data structure, right? So yeah, its implementation can be different, but its operations are similar in any programming language. So pretty much any programming language you ever use has a stack in it, and they're first in, last out. So what does that mean? That means that like for a stack, what you do is you have, for the elements that you have, what you do is you push them onto the stack, and when you pop from the stack, when you take elements off the stack, the first one that you're going to move is the last one you put on. So just looking at this picture, right, we push 2 onto the stack, push 3 onto the stack, push 4, 5, 6. But because 6 is the last thing we push, the first thing we're going to pop is 6. So you can kind of think of it as a representation, like going up, and then you just take from the top. So you put on the top and you also remove. And yeah, you can think of like a stack of dishes. When you stack dishes up, right, last one that you wash is also going to be the first one you use, because unless you take from the bottom, but then you can break all your dishes. So yeah. So a little more on stacks. So common stack operations are push. So this is putting something on the stack. Pop, and this is taking something off the stack. And in different programming languages, they can be called something slightly different, but it's the same operation. Pretty much any stack ever, or every stack is going to have push and pop. And also top, and in Java, it's peek. And that allows you to see what's at the top of the stack. So because with a stack, you only have access to the very top element. And that means, because if you think about it, you're pushing onto the top and you're also popping off the top. You can't do anything with any of the other elements. But you can also look at what the top element is without removing it. And then the last thing you can do is check if it's empty. So you're saying, okay, do I have anything in the stack? And if you don't, then empty or is empty will return true. And if you have something in it, then it'll return false, right? And so some application stacks, you might be thinking, okay, so why are stacks useful or helpful? And so you have depth first search, and this isn't something we'll talk about until later in the semester, but this is one kind of search in like a graph or a tree, in which you just go in one direction until you can't go any further, and then you go back and backtrack through. But don't worry too much about that. We'll talk about that later in the semester. There's also a reversal algorithm. So if you want to reverse a string, like maybe if you think about it, right, let's say that I have a string that's like ABC, and I want to make it like CBA. Then I would put A on the stack, B on the stack, C on the stack. And then when I pop from the stack, I get C because that's on the top, and B, then A. And I reversed it, right? And then function / method call stack. So as I mentioned, the call stack is itself a stack. And we'll look a little more at that later with an example. Expression evaluation. So for checking the number of parentheses, so if you want to say, like, this is kind of common, if you want to see if the parentheses are valid, like if every open one has a corresponding closed one afterwards, you can put the opens on the stack, and whenever you see it close, pop it off the stack. So let me draw that up so you can kind of see what I mean. Yeah. Okay, so as an example, let's say that I have something like this, and I want to see if, like, maybe this is valid in the sense that every open parenthesis has a corresponding closed parenthesis afterwards. So what I could do is I could say, okay, if I see an open one, I put it on the stack, and then I go to the third element. I say, okay, well, I have a closed one, so I remove from the stack, right? And then I have this one, and okay, I remove from the stack. And so I could say, okay, this is valid, for example, but maybe it's something slightly different where I have something like this, and I want to know, is this valid, right? And let's just do something like this. Then I would, again, put on the stack, put it on the stack, remove from the stack, but then I would add another one to the stack, right? So I'd add this to the top when I get here, and then when I get here, I remove from the top. That's still not in the stack. And you can say, okay, stack's not empty, so this wouldn't be valid. In the set, I'm just saying, like, valid isn't like every open has a corresponding close. So this is just kind of a way to solve that particular problem, just as an example of how to use stacks. And then backtracking as well. And backtracking goes along with depth first search. And that's where you will go back to parts of the solution that you haven't checked already. But again, that's becomes more relevant when we talk about like depth first search. And syntax parsing, and that's kind of similar to this whole check number of parentheses. where you're parsing some, well, a string or some syntax. So a lot of times, like different languages use syntax parsing, or like a compiler, for example. Okay, so that covers stacks. If you guys have any questions about stacks, we can talk about it. Otherwise, I'll move on to queues. Okay. Well, if you do, just like, go ahead and ask. So what's a queue? So a queue is kind of like a stack, and then it's also an abstract data type. But it's a little bit different, right? And we can kind of already see from the picture here that there's a difference in that a queue, right? Rather than having both the push and the pop like on the same side, it has enqueue and dequeue, but notice that dequeue is on the opposite side of enqueue. So the way this works is you put something on a queue, right? And then when you go to remove it, the thing that you're going to remove is the first thing you put in instead of the last thing. So they use first in, first out rather than first in, last out. So the first thing you put in is the first thing that goes out. So if you think about this kind of queue, it's the same thing as like a queue, like if you're in a line for food or something like that, the first person served is going to be the first person who ordered, or the first person in line, right? Or the first person who got in line. And the last person is going to be the last person to get in line. And so it's just like a regular queue. And yeah, a buffet line, first person in line, the first person to get in line is the first person to get. Okay, so let's talk a little more about queues, like why would they be useful? Well, first queue operations. So there's enqueue and dequeue. So enqueue is to put something into a queue, and dequeue is to remove from the queue. So dequeue, like you're removing from like the head of the queue, and enqueue you're putting something into like the tail of the queue, like you're putting something at the back, or you're moving from the front. And you can also see what's at the beginning or at the front of the queue, right? Like who's first in line, and check that. Just like with stack, you can check what's first in a queue, you can also check what's first. And that's with just front or Java and speak. And then also empty. So you can check if the queue is empty. And so some applications of queues include breadth first search. So this is another kind of search, which is a little bit different. And again, we'll talk about this actually, we'll talk about it with trees as well. When we talk about trees and graphs. And breadth first search is a little bit different from depth first search, because depth first search, as I mentioned earlier, you go in one direction as far as you can, and then you backtrack. With breadth first search, the idea is you're going in each direction, you're trying each direction just a little bit, and then you go further away, but in each direction. So that's kind of a loose explanation of what it is, but don't worry too much yet. Scheduling algorithms. So these are like if you're trying to assign tasks to maybe different machines or something, you can use a queue because, for example, the first task in the queue, right, I'm going to assign to like the first machine, for example. Like if all the machines are busy, right, then the first machine that becomes not busy, I give like the next task to. So the next task in the queue. So that would be like an example of scheduling algorithm. Handling interruptions in real-time systems. So implementing system interrupts. So this does happen. So if you have a real-time system, right, it needs to know like what to respond to. And so it might have a bunch of things it needs to handle. And so it'll handle them with the queue. Like it'll put it in the queue, like, okay, I need to deal with this, and then I need to deal with this, and so on. And it'll kind of go through them in some order. Maybe they'll get priority, or maybe just like in the order file. Okay, so that's just like a loose explanation of what queues are, like or when to use them. But the main idea here is like common queue operations would be these and how it works, right? So let's quickly talk. Let's like go on to a poll question, unless you guys have questions about it, and we'll see if you guys can kind of get this. If not, don't worry too much because we haven't really discussed in too much detail, I guess. But or we haven't discussed that particular. But first, yeah, let's just do the Menti port. And yeah, this is the Menti code. So go ahead and put it in. And I'll go back to the questions. So I'll put it in the chat as well. That's the Menti code. All right, trying to move this to the other side so you guys can look at this, and I'll go ahead and ask the question. I think you guys should be able to answer now. I guess the first one first. All right. Okay, so I saw some answers. So let's go ahead and do the next one. So let me reset the results on this so you guys can try and answer the next question. Oh, whoops, I think this is supposed to say A, not B. Yeah. And the same thing here. I guess we kind of messed this up. These show A. So try to got confused about that. Oh, if you're on Zoom, you can still join the Menti. Yeah, separate. Okay, and now we'll go ahead and go over these as well. Or go ahead and answer the next one as well. So go ahead and try and answer again. Last one. Okay. And also, since we're here, if you guys want to try and, I'm just going to go ahead and put the password for the quiz or the attendance discussion quiz in the chat now. And if you guys want to take it now or later, as long as it's like during the class period, I'll just go ahead and put it there. Yeah, so this is kind of your cue to take the quiz. So this is the password. Cue, take quiz. To cue to take quiz. So you guys can try and do that. Okay. So maybe still doing that, but I'll go ahead and go over the answers for these. So I saw a lot of answers which were good, but I still want to go over kind of what these are and why they're that, because we hadn't gone over the time complexity of any of these yet. Let's discuss it. Oh, chat first. Sorry. It's a different quiz. I meant the discussion attendance quiz, like discussion, like meaning that you attend discussion. So it's not like the regular quiz. So I'm sorry if like any of you got confused. I started that. It's my mistake. But I just meant like I set up a quiz for discussion attendance, and that's the quiz password for it. You can absolutely take the regular quiz later. Okay. So going over the time complexity for these. Believe it or not, the time complexity for all of them is actually the same. They're all O of 1. And this might seem kind of weird, but if we think about the data structure, right, what we're really doing is we have like, so for example, for push and enqueue, for stacks and queues, you have like some data structure, right? And for pushing, right, you're just putting something in there, right? You have like an empty spot and you're like putting it on there. And for enqueue, it's the same thing. And assuming they have a large enough array, I mean, that'll be fine. So for example, even if you think about this like being implemented in C++ with vectors, right? Just putting something into a vector takes O of 1 time, right? That's really all we're doing is we're just putting, if we implement this with vector, all we're doing is putting it into the vector, right, at a certain position. And for pop and deque, well, we're just, if again, we think about it as a vector, we can think about, okay, for this one, if this is, for example, our queue, this first one here, queue, is our stack, right? With stack, we just access the first element and take it out. And in queue, we just access the last element and take it out. And again, it says with a vector, for example, it's just O of 1. And then the time complexity for front, peak, top, whatever, right? Again, it's just O of 1 because we think about what that entails for a vector, you're just accessing the last element or the first element with a stack. That just takes O of 1 time, right? So all of these are O of 1. Okay. So some more resources on stacks queues. If you have an interest in like doing more practice than like stack, for example. And these will be available. Okay. So linked list. So linked list is the next topic. So for those of you who don't know what linked list is, I would think most of you do. I think this was a project in programming too. So if you don't remember though, a linked list is like you have a bunch of nodes of some type, right? And they're just connected to one another. So like each one has a next. You can also have it like a previous. So all of them are connected to one another, and you don't have random access like you do with like an array. You have to go one by one if you want to access a certain thing. Right? Okay. Does anyone have a question about like linked lists are? All of you know what it is. Okay. Okay, so how can we reverse a link? So this is a little bit tricky, right? So maybe we can think about some things we've already used today. Like what kind of data structure don't we use for reversing things?
A stack.
A stack. Yeah, exactly. Right. So like when we talk about reversing a string, it's a similar idea for reversing a linked list. But we can absolutely use a stack, and that's exactly what we're going to use here. But if you notice, we're not using, there's no mention of like the stack here. It doesn't have to be, because as we mentioned earlier, the call stack is a stack. So if we use a recursive function, we're necessarily using a stack. So you don't have to like necessarily like say, oh, stack. We can still use the call stack as a stack. So, okay, let's just go through an example and see how this works. So we use the recursive call stack because it is a stack. So we can do this recursively or iteratively. So if we wanted to do it iteratively, we could just use a stack variable rather than using the call stack. And yeah, all recursive functions we could do iteratively if we wanted to. So the primary function, right, calls a helper function. So we have a reverse list which calls reverse help. And previous is null because the previous node at the head is null, right, for a linked list. And it takes in previous and current to reverse the connection. And so let's look at the base case. I'm gonna walk through the code in a minute, but let's just see the base case, right? We have our recursive. We have our base case here, which is if current is null, turn previous. So this means that if this is going to happen when we reach the end of the linked list, right? So if we get all the way to the end of the linked list, right, then the next thing, or okay, this is for the head, but it'll be the end of the linked list when we go in reverse. But okay, at the head, for example, right? Oh no, this will be at the end of the linked list because previous is null at the beginning. Okay, sorry about that. So previous is like the node we're at, but then current is the one that follows it, right? More or less. So at the end of the linked list, right, we have current is null. So what that's going to mean is like we've reached the end, right? Because the previous had a value, but this one doesn't, then that must mean like the previous was the last element in the linked list. So current doesn't have a value, so current is null. So we've reached the end. In that case, we return previous because that's our base case. Like if we've gone through the entire linked list, right, and we reach the very end of it, then we're just going to return as our new head, right, the previous, because this is the last element. And then we have a recursive call and step. So if it's not the last element, then we're going to call reverse help again. but this time with like this element and like the next one. So we're moving down in the linked list. And current next is now previous. So this is what allows us to reverse it. So we're saying, okay, when we're currently at its next, so the thing that follows it is the one that came like before it before. So we're just reversing. And we return the new head. So sorry if that was confusing, but we'll go through an example and hopefully it'll be less. So it's O(n) space and time complexity, and we can see a recursive call stack. So let's look at this. So let's look at this example. We have 1, 2, 3, 4, 5. And here we're using the call stack as mentioned. And okay, so the first thing we're gonna do, right, is for this list, we're gonna call reverse list 1 because we are gonna call it with the head of the linked list and null as the previous. Okay, what comes next? So this is our call, right? This is now gonna call reverse help. And then after that, right, what we're gonna see is we're gonna say, okay, reverse help null 1. So when that happens, if current is equal to null, which in this case it's not, right? So we're not going to do this. So we're going to say, okay, new head is equal to reverse help. So this is the first thing we do, is we say, okay, reverse help cur and current. So cur is 1, so we're going to call reverse help. So this method again with 1 and 2, which is why we see this. And if you'll notice, this is going to keep happening. We're not going to get these 2 lines until later. So first, we're only going to like really do this until we reach the end. Once we hit a base case, then we're going to go back to the stack. So how this is going to work, right? Is we call reverse help 1, 2, and 2 also isn't the end. So we're still not going to do this if statement. So we're going to go down here and just do this. Same thing. So we're going to next call reverse help 2, 3. And then because 3 still isn't null, then we're going to call reverse help 3, 4. And again, 4 isn't null. So we call reverse help 4, 5. And same thing again, but this time it's 5 null. So once we call reverse help 5 null, now we get to our base case, right? Where cur is equal to null. And in this case, we're returning previous. So previous here is 5, right? And what this means for us is now we go back up the stack because we finished this call, right? We reached this. And so that means the last time we called reverse help, we get the result. Like before, when we said new head equals, we got this result, reverse help of 5 null, and it returned 5. So now we go back to this call here, and now we're going to replace this with 5. So let's go to the next slide so we can maybe see this more easily. So we hit the base case, return 5, and now we set new head equals 5. So the way this is going to finish is this is going to go ahead and be 5. We set new head to 5, and current next. So remember, current in this call in particular was 4. Or sorry, 5. My bad. 5. Previous was 4. Sorry about that. It's 5, right? So current's next is previous. So what that's going to do is it's going to say 5's next becomes 4. And then we return new head. And here, new head, remember, is 5. So we return 5. Okay? And so when we return 5, well, that means with this call, remember when we made this call, we also had set new head equal to something. We set it equal to whatever this one returned. Well, this one returned 5. So the same thing's going to happen. We're going to have a 5 here. But it's for this function call. Move on to the next slide. Is everyone following so far? I feel like it might be a little complicated, but you guys kind of get it? Or if you have any questions, just cool. So now we reverse help 3, 4. And remember, this returned 5 before, so we have 5 here. So new head is equal to 5. And current's next is equal to previous. So remember, current in this case was 4. So 4's next becomes 3. So now we have 4, 3. And remember, we already had 5 to 4, right? So 4's next becomes 3. So we have 5, 4, 3. And then we return new head. Well, new head was still 5 because this is what this returns. So we have 5 here. And so now when we call this one, again, on this line, we're going to have new head equals 5. And we go back up again, and we have new head is 5. And the same thing happens, current's next becomes the previous. Well, current was 3, right? And its next is now the previous is 2, right? So now we have 3, 2. So 5, 4, 3, 2. And new head again was 5, so we're going to return 5. And again, we have new head becomes 5 again, and current's next, so 2's next becomes 1. So now we have 5, 4, 3, 2, 1. And then we reach this case here, we reverse help no 1. And in this case, 1's next is going to become null, because again, we have reverse help 5. Current's next is previous, so that was just 1's next becomes null, right? Because in the initial call we had null and 1, so now it's 1 and null. And then we return 5. And now, finally, we've gone through all of the reverse help calls, and so that's going to be returned to this first method here. And so when we originally called return reverse help null head, what we're going to end up getting is what this whole thing returns, which is 5, 4, 3, 2, 1 null. So it's the reverse of this. So another technique we're going to talk about is slow pointer, fast pointer. So we're running a little slowly, so I'm going to try and speed up a little bit. But so this is a pretty common technique. So it's kind of important. So the idea of slow pointer, fast pointer is you have a fast pointer which like runs ahead and a slow pointer which goes through it more slowly. But you might only need like one pass, which is kind of nice because oftentimes with slow pointer, fast pointer technique, there might be another way to solve it, but this is often the best way to solve it. So what is it? So you create 2 pointers to iterate through a linked list. So you have a slow one and a fast one. They both originally pointed to the start of the linked list. So you have one fast and one slow. And the slow pointer moves one node. For example, the slow one might move one node for every 2 nodes of the fast pointer, right? And so this might allow us to find, okay, if we did this, for example, what might this allow us to do? What would this yield? Can you maybe think about what this would do? Have 2 pointers, one move, 2 for every 1 the other move. What's the slow one going to point to at the end?
The middle?
The middle. Yeah, exactly right. That's exactly it. Because if one moves twice as fast as the other, and the fast one reaches the end, right? Then the slow one will be halfway to the end. So it'll be in the middle. Oh, this PowerPoint should be on the module, on your modules, like module 3, I think. Yeah. Yeah. So yeah, it's helpful. It's gonna be really helpful when you don't have the linked list because you can't just say, oh, until I reach this point. So you might just have to do this in general. So it's pretty helpful to use slow pointer, fast pointer, for example, when you don't know the link. Okay, so let's apply it, this whole idea, and remove the nth node from the end of the linked list. Okay, so this is the problem. If we want to, given a linked list, remove the nth node from the end of the linked list, and we're trying to set. So maybe some things we can think about when we're trying to do this problem. We want to note that n equals 1 represents the last node in the linked list. So let's look at this example. If we're given this linked list 1, 2, 3, or 5, and it's 2, so what we want to return, we want to remove the second node from the end. So second to last node, and that's the 4, right? So yeah, slow pointer, fast pointer is not the only solution to this problem. But can anyone see like maybe how we could use slow pointer, fast pointer for this? If you don't know, that's okay. Well, that's why we're here, right? Because we don't know everything. So let's go ahead and try and figure this out. Okay. So yeah, one solution, we can use 2 passes to go through the linked list. But if we want to remove the nth node from the end of linked list and only 1 pass, then our really only solution, if we don't know the length of the linked list, is to use slow pointer fast pointer. And in this, if we don't use slow pointer fast pointer, the other approach, which takes 2 passes, we find the number of nodes n. And then the next pass, we find the nth node from the end. And okay, it's still low event time, but it requires 2 passes. But this solution only requires 1 pass. So let's talk just briefly about what the solution might be like, right? So let's say we have a linked list here, and we don't know how long it is, right? But we want to remove the nth one from the end. What we can do, right, is notice that if we have a slow one that points here and a fast one that points here, right, slow and fast, then we can just move the fast one ahead n places, right? So it's going to now be like here, somewhere in here, right? That gets kind of messy. So let's just undo so it looks neater. So move the fast one n places ahead. And then once we do that, we start moving them both at the same speed. So notice the fast one is going to be n ahead of the slow one. But now that we're moving each of them exactly 1 at a time each, then fast will be at the end and slow will be n behind it. So what position are we going to have the slow pointer in? Well, end minus n, right? And then we can just remove that element. And so I realize now it's probably kind of hard to see there, but yeah, the idea is that we move fast and ahead of slow, and then move them each 1 at a time. And then some implementation details might be kind of tricky, but that's the main idea. So slow pointer, fast pointer is not a silver bullet for all linked list problems. You can't always use it, but often it is very helpful, especially if you don't know the length. And you need to think critically about when to apply it, because sometimes it's not right, but often it is. And here's the optimal solution. So let's look at the code. So I want to remove the nth node from the end. So it looks more complicated than it is just because we need to make sure that I also have some edge cases. But the idea is still the same as we discussed, where you just move the slow or the fast ahead spot. So here, well, fast is not null, right? So as long as we haven't reached the end of the linked list, because that's also possible, right? Is the nth node from the end of the linked list is like the first one, right? Like the head. So we may have never actually get like n away from the beginning. So we may never actually have to trigger that condition. But once we reach count is greater than n, then we start actually advancing our slow pointer. And then we also, each time we're still advancing our fast pointer. But once we've actually reached that length or distance between them of n, we can advance them both. And so that's really about it. And then once we actually reach n is count, right, then we're going to start advancing the head. Otherwise, we are yeah, if we have n is equal to count, right, then that means that we reached that point. So that's when we start advancing ahead. But that's also in the case in which the head is the nth node from the end. So that's, in that case, we're just like basically getting rid of the head element. Okay. And just looking at what this looks like, given the nth node exists, we have our method header, input and output, count variable, and we only move the slow pointer as I mentioned if the fast pointer moves n nodes ahead. This is the edge case where the head is the nth node, and here we remove the nth node. So remember, to move the node, we just kind of have to skip it. So we're saying the next element is like the next, so we're just skipping over it. Okay, and looking at this example, right, with our edge case, only 1 node in the linked list. We can just see like fast is the head, slow is the head, and count is equal to 0. Null, head, and 1, and n equals count, right? So we've reached the end. But more importantly, the head is the nth node from the end. So in that case, we say head equals head next. Head's next is null, so we have head is null, and we return null. And we can go through this example as well. We're running a little short on time, so sorry about that. And so we can kind of briefly go over it. N equals 3. So this is referring to, third from the end, not node 3. So that means it's, in this case, 1, 2, 3. So we're removing 2. So fast is 1, right? Slow is 1. count as 0. We haven't reached this condition yet, so we don't advance the head, or we don't advance the slope learner yet, we only advance the fast one. So fast is 2, count as 1. Fast is 3, count as 2. And then fast is 4, count as 3. So at this point, we can't start advancing it yet. Once it reaches the next thing, then we advance it. So yeah, in its last iteration, fast moves from 4 to null, and slow moves from 1 to 2. Count becomes 4, exit while loop with fast is equal to null, and slow is equal to 1 node, and count is 4. And yeah, here we're going to go into else condition, and so slow is next, is going to be the next, so we're going to skip over. So actually, yeah, sorry, we don't advance over 2, we're just going to skip it, right? So we're skipping over the 2. And it's going to look a little bit like this, 1, 3, 4. Then we return. Okay. Hopefully that makes sense. Okay. So now this is something we quickly talked about a minute ago, and we had a discussion about it, right? Is for given the head of a linked list, right now we're going to find the middle. So we can, before we go ahead and jump in and talk about how we would do this, like we did a minute ago, we can clarify some questions. Is it doubly linked list? You might want to ask these, right? Like if you're doing a technical interview, these are some questions you might want to ask. Like, is the list doubly linked? Will the head ever be null? Are there any time or space restrictions? So this gets you an idea of like what they may be looking for when clarifying, so they can kind of see what you're thinking, right? And what if the linked list has an even number of nodes versus an odd number of nodes, right? And so this is kind of important, where it's 1, 2, or 1, 2, 3. And here, if it's even, we give the one right after it, or we give the larger middle. Okay, so finding the middle, it's kind of like we talked about before, is we just move the fast twice as often as we move the slow one. So here, what we're doing is we're only moving the slow every other time. So rather than in the while loop moving the fast twice and moving the slow once, we're just moving the fast once each time through the loop, and the slow every other iteration of the loop. And this will give us exactly that. So we have a control variable and our while loop, and we alternate the control variables to move slow every other iteration. And then that means that we'll have slow in the middle at the end, because fast moves twice as fast. So for example, we have a null head, it won't enter the while loop. If we have only one node, it enters the while loop for one iteration. Slow doesn't move, so it's just going to return slow, which is the head. So far that's right. For our example 1, 2, fast is 1, slow is 1, move slow is false. So in this time, our first iteration, fast is going to be 2, and slow stays 1. But then we actually say move slow is true. That means the next time through, we are going to move our slow one. But here fast becomes null. But because slow is true, we actually do advance slow. And slow is 2. And then we exit the loop because fast is null. And 1, 2, 3, it's a similar example. So let me just skip over it. Sorry, we're running a little low on time. You guys can take a look at that, but it's the same idea. Does anyone have any questions, by the way, about anything we talked about? Yes, kind of following. Okay, cool. Debugging review. And so I think we're not going to have time for the catch 2 stuff, but I'll just talk about debugging really quickly. Purpose of debugging, as you guys may know, is to detect and remove existing errors. So if you have errors, to catch them, and allows you to walk through step by step. So this is kind of helpful because Visual Studio has some really nice debugging tools, so it's easy to use. It allows you to see how a program runs, and let's get started. Okay, let's skip over this poll question because it's not really relevant. It's just talking about when you might want to use a debugger. So basic tools available with debugging. These are kind of the things you'll be using if you want to use a debugger, are breakpoints. So this is like you'll click next to the line number, and it'll allow you to stop there and yeah, pause the execution in the middle of the code, which is really nice because you can see exactly what the variables are at that point. Step into allows you to like go into a method. Step over allows you to like skip over a line of code that would enter a method. Step out of is like if you're in a method, you can just like leave it. And continue just allows you to continue the code until you reach the next breakpoint or exception or finish. And yeah, as we mentioned, VS Code is the preferred text editor for this class. If you haven't set it up already, I suggest doing that. It's really nice for debugging tools, and there are a lot of like extensions with VS Code you can explore. And so for coding in VS Code, so it's technically not or Visual Studio Code is an IDE, but Visual Studio Code is not an IDE, but Visual Studio is. But yeah, in this class we're mostly using Visual Studio Code, which is not an IDE. But it is still from Microsoft, it's still for C++, and yeah, it's pretty helpful. It's text editors. And so some debugging tutorials I'm up there and useful videos. And sorry that ran a little long. Hope you guys stayed with me till the end. And if you have questions, of course, like you can send me an email or message me on Slack or anything like that. But you have a quiz due tonight, and that's the regular quiz by 11:59 p.m. So make sure you do it. Thank you all. Have a nice week.
Thank you. Have a good day.
Thanks, you too.
I'm not from your section, so I don't think I could access the discussion, the attendance
Oh,
thing.
yeah, I did it.
Thank you. Have a good one.
Thanks, you too. What's your name, by the way?
Fatima,
Okay, you should be able to do it now.
all right. And we're just doing
Oh, also, I took the discussion last week, but I forgot to do the quiz.
Okay, yeah, I can put you in. I remember you were here, I think, right?
Yeah.
Okay, what's your name? Sorry.
So with that,
Betta? Or-
yes.
Okay, all right, I can put that in.
Oh, okay. Thank you.
Or actually, it might be easier if I just like open it up for you.
Okay,
Okay.
should I, is now okay, or?
Yeah. That should be fine. Um,
Also, do you recommend these? The Epic right now, and I think for Stack and Q, I'm having a little bit of trouble with it.
uh,
We could